everybody, and welcome to another Back to Basics video. This one, although I have a lot of information here on the board, is actually going to be fairly quick. We're just setting some ground information for upcoming videos about semiconductors, diodes, getting into doping and all of the complicated things that you have to understand when we start learning about diodes. But in order to get into that, we have to learn a little bit of chemistry and the way electrons are passed through materials when we're sending current through them. Now, in electronics, we have three sort of categories of materials that we work with. We have conductors. These are what we use when we want electricity to flow easily. Then we have semiconductors, which are used in the case of, in this case I've chosen carbon, but silicon is also a very common semiconductor. And they're materials that sort of resist electric flow. And then insulators, which inhibit electrical flow. Now, I've chosen to use the Bohr electron model here, which is out of date and kind of incorrect. The actual way electrons are arranged in an atom is sort of a fuzzy cloud with no defined levels where the electrons are just sort of zipping about. But in this case, the Bohr electron model helps us understand a little bit better what's going on. So for the purpose of simplicity, we'll go with this. Now, a very common and the most used conductor out there would be copper. Now, copper has 29 protons, 35 neutrons, and 29 electrons. I should have remembered that, but I had to do the math in my head real quick. Now, the number of protons and neutrons don't really have any bearing on a material's ability to conduct. It all has to do with the electrons, and most specifically, it has to do with the outermost layer of electrons. Now, in the case of copper, we've got 4 electron energy shells. The first energy shell has 2 electrons in it, which I've drawn there. The next energy shell has 8 electrons, which is that next line of dots. The next energy shell has 18 electrons, which is the really big one here. And then lastly, the fourth energy shell has 1 electron, which makes copper a very, very good conductor, because this one lonely little electron, it's not very well bonded to the atom. So it likes to go off and do its own thing. That's why copper sticks to oxygen really well and turns green, and you get copper oxide. This electron is what enables us to use this as a conductor. You stick a bunch of copper all together, you have all these electrons that are loosely jumping about between copper atoms, wandering around, and then if you induce a current across the copper, an electron will come along and bump this electron, and that electron will bump to the next atom, and that electron will bump to the next atom, and it just bumps on down the line. And instead of one electron flowing through the circuit, you just have a bunch of electrons shifting down the line. And so that's why copper, silver, gold, anything with 1 electron in its outer valence will be an excellent conductor. Let's move down to carbon, which is classified as a semiconductor. Carbon is very commonly used in resistors, metal film or carbon resistors. Metal film resistors are different. I'll talk about those in another video. Anyway, carbon is a semiconductor. Now, carbon has 6 protons, 6 neutrons, and for its electron shells, in the first electron shell we have 2 electrons, And in the second electron shell, we have 4 electrons. Now, carbon, it'll loan out an electron if it is made to, but it doesn't really care one way or another. It likes its 4 electrons, it holds on to them, but not too tightly. So in the case of resistors, it's a little bit harder to kick those electrons off of the carbon atom in order to get the current to flow through, but it's not too bad. And the same thing will happen. An electron will kick off and bounce an electron off the next atom, which bounces an electron off the next atom, and so on and so forth. But it's a little harder to do that. And that's why carbon resists current flow. Then, as far as an insulator, there aren't a lot of elemental insulators out there. A very common insulator is glass, which is silicon dioxide, which is a silicon atom with 2 oxygen atoms stuck to it, and I'll go into it a little bit more when we, well, I guess I may do another video on insulators specifically, maybe, to talk about actual molecular structure, but basically, when you take the 2 oxygen atoms and you stick them to a silicon atom, you get silicon dioxide, which is also known as sand. And they're all sharing enough electrons that their outer valences are filled. And therefore, they don't want to give up any electrons at all. It's very, very, very hard to get them to give up electrons. So that's why they act as insulators. But for the case of an elemental insulator, I picked chlorine. Chlorine has 17 protons, 18 neutrons, and yes, I actually did draw the correct amount of dots in the center of these atoms just for fun. And then the electron shells, the first electron shell has 2 electrons, the second electron shell has 4 electrons, and the third electron shell has 7 electrons. Now in the case of chlorine specifically, chlorine really likes to hold on to its electrons. It will not give up electrons, and in fact, it wants an 8th electron so badly that it will rip electrons off of other elements very violently. That's why chlorine is so massively reactive. You put it in the case in the presence of anything that has an electron to give up, and the reaction is very energetic. But if you try to induce a current through chlorine, you're going to have a very hard time doing it because chlorine does not want to give up any electrons. And in fact, if you have a tube with chlorine in it and you have an electrode on one end and the other end, and you start trying to feed electrons through it, it'll just eat the electrode. And no current will flow through it. But the point is that the more electrons you have in your outer valence, if that outer valence is filled with electrons, it is going to be highly resistive if completely inhibiting electron flow at all, as is the case with silicon dioxide. The outer valences are completely filled, and therefore it will not conduct electricity. Anyway, the next time we talk about semiconductors, we'll be talking about doping and pentavalent and trivalent semiconductors, and that will lead us into talking about diodes, and then we'll start talking about transistors, and we're starting to get into the more complicated stuff here. Now that we've got the basics down, we're going to start getting into the more advanced basics, as contradictory as that sounds. So anyway, thanks so much for joining me for this. Feel free to start a discussion in the comments below. I know I overlook things. There are things I take for granted. So if I left something out or if I made something unclear, let me know in the comments below. I will clear up your questions there. If you haven't already, consider subscribing here. I'm almost halfway to being able to monetize again, and one of these days I'll have 1,000, and then I can stop begging for subscribers. But anyway, that's that button there. Here will be a video that YouTube thinks you'll enjoy based on your watching habits, Over here will be the Back to Basics playlist, and right here will be a link to my Patreon in case you decide you'd like to send me a couple bucks a month to help support me making these videos. Thanks so much for watching, and we'll see you next time. Bye-bye.